there is something called the autoionization of water. And it looks like this. H2O can break down to make hydrogen ions and hydroxide ions. And that equilibrium reaction represents the autoionization of water. Another way that could be written would be to write two waters making H3O positives. Do y'all remember what those are called? Hydronium. Remember we introduced that term last time, and I said that we'll use it a lot in this chapter. Hydronium ions and hydroxide ions. Okay? Those are just two ways to write the same thing. So in other words, since both of those mean the same thing, y'all, a hydrogen ion and a hydronium ion, those things are used interchangeably. You can write either one and it means the other. Okay? Since these are equilibrium reactions, then they would have an equilibrium constant expression. Remember doing that last time? What does that mean? An equilibrium constant expression. That's kind of a big thing to say. Yes. Equilibrium constant expressions are products over reactants raised to the power of the coefficient. Right? What would the equilibrium constant expression for this first reaction look like?
It's not aqueous, so you can't put it over. I mean, it's a liquid, you can't use it, right?
Well, wouldn't the equilibrium constant be equal to the concentration of the hydrogen ion times the concentration of the hydroxide ion? And wouldn't that be over nothing because the reactant's a liquid and we don't include liquids in the equilibrium constant expression? Right? Okay. What would the equilibrium constant for that second one look like?
The same,
Yeah, it's the exact same except for we would put the hydronium ion times the hydroxide ion. Okay? So again, y'all, both of those are saying the exact same thing because a hydrogen ion and a hydronium ion, those symbols are used interchangeably. Now, these are equal to an equilibrium constant. And when we did chapter 15, we used labels for K. When I started, we called them KEQs, right? It was a K with a little EQ subscript. And then we talked about the difference between a KC and a KP, right? Where C's is when you use molar concentrations and P's is where you use pressure, okay? Here, when we're specifically talking about the equilibrium constants that show the autoionization of water, these get a W designation. A KW is equal to the hydrogen ion times the hydroxide ion concentration, and the W just stands for water, okay? Throughout this chapter, everything that we talk about in chapter 16, and I think even in chapter 17 as well, you know, all the reactions are happening at 25 degrees Celsius, which you guys know is room temperature. Okay? So at 25 degrees Celsius, Kw will always be equal to 1 times 10 to the minus 14. That's always what Kw will be equal to. Because we're going to maintain 25 degrees Celsius in these chapters. And we talked a little bit last time before we introduced this chapter, and you guys coming off of taking the take-home test, about pH and hydrogen ion concentration, hydroxide ion concentration, and what that means. Y'all know that pH is a measure of the concentration of the hydrogen ion, right? And if the hydrogen ion concentration is greater than the hydroxide ion concentration, then that means the solution is acidic. If the hydrogen ion concentration is less than the hydroxide ion concentration, then that would mean that the solution is what? Basic. If the hydrogen ion concentration and the hydroxide ion concentration are equal, then what does that mean? Neutral. And so in a little bit, we're going to relate these values to pH, but you guys know that acidic means what in terms of pH? Lower than 7. Basic means greater than 7, and neutral means 7. Okay. So if the autoionization of water always looks like Kw is equal to the hydrogen ion concentration times the hydroxide ion concentration, then if I know one of those, I can calculate the other. Right? Because Kw is always 1 times 10 to the minus 14. So, let's calculate the concentration of the hydroxide ion in a solution that has a hydrogen ion concentration of 1.2 times 10 to the minus 3 molar. We know that Kw is 1 times 10 to the minus 14. The problem tells us that the hydroxide ion concentration is 1.2, bless you, times 10 to the minus 3 molar. So when I divide those out, I get, where am I going to write that?
You're looking for the hydroxide.
Oh, I sure am. It's not going to matter as far as what I had, but to set it up right. So X is equal to the concentration of the hydroxide, which we said is 8.3 times 10 to the minus 12 molar. Is this solution acidic, basic, or neutral? Yes, it's acidic because a hydrogen ion concentration of 1.2 times 10 to the minus 3 is a lot bigger than 8.3 times 10 to the minus 12, right? You've got negative exponents. So that would be an acidic solution.
Where do you get that 8.3 times 10 to the negative 12?
Say 1 times 10 to the minus 14 divided by the 1.2 times 10 to the minus 3. Okay? Now, can I switch slides for a second and go back? Guys, in pure water, if this is your autoionization constant for water, in pure water, H and OH are equal to each other. Okay? What is that saying? What is the pH of pure water? It's 7. So the pH is 7. What would the hydrogen ion concentration be in pure water? What would the hydroxide ion concentration be in pure water? They've got to be the same. They have to be equal. It's not half of this. If this is X and this is X, and that's X squared, then the square root of this is what? What's the square root of 1 times 10 to the minus 14? Huh?
1 times 10 to the negative 7.
Yes, in pure water, the concentration of hydrogen would be 1 times 10 to the minus 7, and the concentration of the hydroxide would be 1 times 10 to the minus 7. They would both be equal. Okay?